All right, so next is concurrency control. So the big thing with a skip list, no pages means no latches. And so what that means is you can actually implement the underlying data structure skip list to be lock-free. We also have MVCC and MemSQL where every node is a lock-free linked list. So the skip list is a skip list of lock-free linked lists. Each lock-free linked list is a lock-free linked list of versions. Now you still do need row locks to implement pessimistic concurrency for things like read committed isolation. And we have row locks in MemSQL, but because it's all in memory, we can use these futexes, which are a cool Linux primitive that only cost 4 bytes and give you very, very performant row locks.
Have you found that futexes work as well as like writing your own spin lock?
Oh yeah, yeah. Futexes in the common case aren't a system call.
Right, but if you block, you have to go down the kernel, right?
You do, yeah. And for row locks, that trade-off appears to make sense. We do have spin locks in MemSQL for other locks where spin locks do make sense. Yeah. And basically, kind of with these building blocks, we're able to implement read committed and snapshot isolation in MemSQL very straightforwardly. So that's it. Concurrency control, we can dig in a little bit more. Go ahead.
Repeatable read, right?
No repeatable read. Read committed and repeatable read are different. Okay. Yeah, read committed is a less strict isolation level than repeatable read. I think people argue snapshot and it's not clear whether snapshot or repeatable read which one is stronger. They have kind of different semantics, but
They have different anomalies.
Yeah.
Orthogonal.
Yes, orthogonal.
Like these branch pop and they both go serialized.
Yeah.
So do you have the assumption that for every table should have at least one index, or should have at least probably one primary index?
I did not understand the question.
This question is like in like do you require that every table have at least one primary key index?
Oh yes. So every table has a primary key, and if you don't specify a primary key as a user, we'll create a fake one under the hood for you in the row store, not in the column store.
So every operation should happen with the index, right? I mean every operation should go through the index, right? You do not support sequential scans.
The two statements that you claim to be contradictory are not contradictory. So you can sequentially scan a primary key.
Okay.
Yeah, and if you don't specify a primary key, then rows have an implicit primary key whose value is the order of insertion.
Okay.
Yeah. So essentially, we map the case that you're talking about to having an index. All right, in-memory column stores. So the first rule, we don't believe in this idea of pure in-memory column stores. Why? So column stores have big sequential scans and writes. And column stores are built on huge immutable vectors of data. So what does this mean? It means you should cache the data set in memory. Why did we care about pinning the data in memory with a row store? It's so that we could use pointers to glue rows together. And if you use pointers to glue rows together, you get all of these benefits that we just talked about, like lock-free and efficient online alter. With a column store, you don't really have pointers taking you from row to row. You have huge vectors of data. And paying something like, is this vector of data in memory or on disk per 100,000 or million values is negligible. And so the cost of actually supporting something which spills and operating over a cache is negligible in the context of a column store. So then the question is, how do column stores benefit from living with an in-memory database? Or why is sort of the MemSQL column store have some advantage over a classically built disk-oriented column store? Well, the answer is we can actually use the lock-free skip list to help us quite a bit. And there are two ways that we do it. The first is we keep metadata in memory, and the second is we basically have a sidecar row store, and I'll explain this in a little bit more depth, for fast small batch writes. So the big thing in MemSQL that we really care about with the column store that distinguishes our column store from every other column store is very, very, very fast writes. And again, I said earlier, the workload that really sets us apart, or one of the workloads that really sets us apart, is real-time analytics. And what do you think really matters in real-time analytics? It's very, very, very fast writes, especially on small batches of data. So this is what the metadata in the column store looks like. I think you covered column stores, and the general architecture of a column store is to have what are called segments or groups, or I don't know what term you used, of rows, row groups of where you kind of take a group of rows, split it up into columns, store each strip of columns with encoding and compression, and then keep around some statistics for each chunk of columns that you stored, which tell you what are the minimum value, maximum value. You can have some other cooler statistics like give me a Bloom filter over these values, et cetera. And operate on this metadata to basically figure out which segments you need to read and kind of where these segments are. So in MemSQL, these segments are actually stored in a lock-free skip list. And that means that operating over these segments can be done really, really fast. So in a lot of systems where you have this metadata on disk, if you need to do something like count the number of rows or find the minimum value for a column in a table, or even figure out which of these things you need to open up at all, you need to read from the disk to kind of read these metadata values. In MemSQL, this is all done very, very quickly in a lock-free skip list. The other advantage is that each of these kind of segments that are pointed to by a row in this metadata are immutable. And what that means is when you write more data into the actual columnar storage, you write a new immutable chunk of data. And kind of the mutable thing that you need to modify is the skip list. And the skip list is lock-free. Therefore, the implementation of the column store with respect to writes is also lock-free. So having this kind of metadata structure, which is very, very mutable in memory and very fast, actually has a number of advantages in a column store. Now, to understand the second benefit, which is that sidecar row store, we need to look at kind of how does the column store look to begin with. So in MemSQL, the column store is this thing called a log structured merge. And it kind of looks like this. So this is a table, this is kind of a log structured merge of an integer column. And you can see that there are non-overlapping runs of data. Each run is sorted. And you could compute kind of an overall sorted view of this table by doing something very similar to merge sort. So you look for the minimum value across these runs. It's 1. So you pick 1 or you pick this one, it doesn't matter. Return it, and then advance to the next segment here. And you can use that to kind of construct an overall sorted view of the data. And if you read about LSMs, you'll find that LSMs have tunable trade-offs for read and write amplification. So the more of these things you have, the faster writes are, but the slower reads are. That kind of makes sense. You're looking at more of these chunks. The fewer that you have, the slower writes are, because say you write 25 in this one, you need to kind of insert it right here, which has implications for this half and this half of the log structured merge. So writes are slower, but reads are obviously faster. Now, LSM on its own enables fast writes to a column store, because what it means is every time you write to the column store, you don't need to think about potentially resorting an entire log structured merge of, or an entire sorted run of data. You can kind of insert to the smallest sorted run, which is larger than the amount that you're inserting. And so that actually, from the perspective of relatively small batch writes, is very impactful. And if you think about it in terms of absolute numbers, if you have one huge sorted run of a column store, you can probably write to that thing once a day. And that's a pretty common pattern with sort of large sorted data warehouse implementations that we see. With just the log structured merge implementation, you can probably write to a column store something like once every several minutes or once every hour. So it gets you a lot of the way there, but it doesn't let you write to something maybe every few milliseconds or every second. But if you make the smallest sorted run a lock-free skip list, you can actually do some interesting stuff. So in MemSQL, it kind of looks like this, where you have bigger sorted runs of columnar data, and the smallest sorted run is actually a lock-free skip list. And this lock-free skip list you can write to incredibly quickly. In fact, exactly as quickly as you can write to the in-memory row store in MemSQL, which is able to process something like 1 million transactions per second on a pretty weak machine. And what's really cool is taking batches of data from this skip list and writing them to the column store is about as fast or even a little bit faster than writing to the skip list to begin with. So batched operations from this row store to this column store are very fast and can actually keep up with singleton writes to this row store. So what does that mean? In MemSQL, you can actually run singleton inserts into a column store table, and as fast as your SSDs will take it, we can actually, in the background, flush that to a column store very, very quickly. And this is kind of the thing that enables MemSQL to work very well for real-time writes into a column store. And that is very, very significant for real-time analytics.
But you don't have to flush to the LSM for durability because you're ready
No.
to log in.
Yeah, we're going to talk about that in just a moment, yeah. So this model also extends very, very nicely with durability.